Hello everyone, and welcome to a relatively short discussion of Newton's third law of motion. Now, yesterday we did an activity in which you did a lot of interactions between objects. You pushed, you pulled, you interacted, had the objects interact through the magnet ends, so you had long-range forces. And in each interaction, you measured the forces of interaction. You measured the force exerted on one cart and the force exerted on the other cart, and you compared them. And in each and every situation, you found a pattern. Namely, the forces exerted were always equal in magnitude and opposite in direction. This is Newton's third law. Now, one thing you'll notice about it is that there's no exceptions. It doesn't say except when this happens. If you think about the examples we did, it didn't matter what the relative masses were. One mass could be bigger than the other. It didn't matter their velocities. It didn't matter whether they were accelerating or moving constantly or not moving at all. It didn't matter whether they were pushing or pulling on one another. It didn't matter what angle they were at. It didn't even matter whether they were touching. As long as they interacted with one another, long-range forces like the magnet ends, you still ended up with always equal and opposite forces. This is one of the most straightforward mathematical laws we'll look at all year that is one of the most difficult ones to accept. But hopefully that activity yesterday kind of pounded it in your brain because you did lots of examples and they were always, always, always equal and opposite. Now this is not the definition you normally see. That's the one, the more pithy version you see. For every action, there is an equal and opposite reaction. Now, that's kind of a literal translation from the Latin in which Newton wrote at the time, but it can be kind of confusing. There wasn't a good word in Latin to mean what we now mean as force. So really, if we translated this a little better, it would be for every force, there's an equal and opposite force. Action and reaction can sometimes lead to some confusion as to effects of forces and the forces themselves. And we're going to look at that a bit tomorrow. I'm going to do some demos for you to try to get at that. But for now, before we go there, let's take a look at some other little complications that can creep in. Since the math is simple, there's also some complications, though, conceptually. And we're going to look at these complications with a wonderful story. A Newton's third law story about a horse and a wagon and a farmer. So, farmer comes out in the morning, wants to go to market, hooks his horse up to a wagon, hops on and says, "All right, giddy up, horse. Let's go to market." But this isn't a dumb horse. This is a smart horse. This horse can talk. So the horse turns around to the farmer and says, "Hey, look, I know by Newton's third law that if I pull on the wagon will pull on me, and it will exert an equal and opposite force." Newton's third law, right? I mean, we did that tug of war yesterday, and we saw that the forces of interaction were equal and opposite. Well, if you add up two equal and opposite forces, they cancel each other out. And therefore, there would be no net force. And if there's no net force, I won't accelerate, so why even bother to pull? Now think through his logic again. If I pull on the cart will pull on me with an equal and opposite force. That's true. Right? Equal and opposite forces would add up to zero, and therefore no net force and no acceleration. So why even bother to pull? Now obviously something is wrong in that little paragraph there, because otherwise, a horse could never walk to market. Well, if you can't see what's wrong here, let me help you out a little bit. Let's look at the horse and the cart as separate things. So the horse pulls forward on the wagon. By Newton's third law, what would the wagon do? It would pull backwards on the cart. Backwards on the horse. Right? And those forces, forces of interaction, would have to be equal in size and opposite in direction, which is exactly what we saw in the little tug of war section of our Newton's third law activity. So the horse is definitely right about that. However, how many of those two forces act on the wagon? And how many of those two forces act on the horse? Well, hopefully here you're saying one acts on the wagon and one acts on the horse. Well, there you go. If only one force acts on each object, then they can't cancel out. In order for two forces to cancel, they have to both act on the same object. And so that's something that's always going to be true of Newton's third law pairs. They may certainly, or they actually always are, equal in size and opposite in direction, but they never cancel out because they act on different objects. One force acted on one cart, one force acted on the other cart yesterday. One force acts on the wagon, one force acts on the horse. So the farmer explains that to the horse, and the horse says, okay, I'll give you that. Forces won't cancel out because they don't act on the same object. However, look at the diagram. If I pull forward on the wagon will pull backwards on me. So how will I end up moving forward to market? Oh. So the horse is again using something that's true, trying to question the farmer here. So I pull forward on the wagon pulls backwards on me. Well, hopefully some of you are screaming at the screen, hey, wait a minute. I know there's more going on than just a horse pulling on a wagon and a wagon pulling on a horse. There's more interactions going on here. So let's look at our 3 interacting things. And actually 4 if you think about the surface and the earth as being separate things. Now, the earth pulls down on the horse with a force of gravity. So by Newton's third law, if the earth is pulling down on the horse, what's the horse doing? That's right, the horse is pulling up on the earth with an equal and opposite force. Now you might say, well, that's a little weird. And yeah, I mean, we haven't drawn that force before, but that's because we've always been concerned with the box, not necessarily drawing the forces on the earth. But Newton's third law says those forces of interaction are always there. And as we saw yesterday, even if the horse isn't touching the earth, those forces of gravity still exist, right? Long-range forces, just like the magnetons. So there's one interaction. Now something else that's going on. Of course, the earth is supporting the horse, or the surface, if you will. So the ground is pushing upward on the horse with a normal force. But what's the horse doing? That's right, it's pushing down on the ground. So we've got this other little interaction, and notice I'm color coding them here. Right? So we've got the horse pushing down on the ground and the ground pushing up on the horse. Now, there's one other thing going on here. Think about walking down the hallway or something like that. Try walking down the hallway by pushing down on the ground. Try it right now. Stand up. Push down on the ground. Can you go forward? It doesn't seem to matter how hard you push down on the ground. You cannot go forward. What do you have to do to go forward? You have to push down and backwards. Because if you push down and backwards, the ground will push up and forwards on you. And by the way, that's a force of friction. That's a helpful force of friction. Right? If you're on ice, you can push down on ice, but you can't push backwards on ice. Your foot would just slip. Right? So you need some friction. So sometimes friction can actually propel you forward, as in this case. So these are all of the interactions now going on between the horse, the cart, the earth, and the surface. So let's focus on the horse a second here. If the horse wants to accelerate forward, or rather if the farmer wants to convince the horse that it can accelerate forward, then this force of friction with the ground has to be larger than the force of the cart or the wagon pulling backwards on the horse. Okay, so the force of the surface pushing forward on the horse has got to be greater than the force of the cart pulling backwards on the horse. Now, what does the horse have to do to make that happen? Here's the weird part. Right? In order to get the surface to push forward on the horse, it has to push backwards on the ground. So, the horse has to push backwards harder on the ground than it pulls on the cart. And if it does that, then the ground will push forward on the horse harder than the wagon pulls backwards on the horse. There'll be a net force forward, and the horse will accelerate to market. You might need to rewind that and listen to that little bit again, because I'm certainly not going to try to say it. But let me give you another example that might clear this up a little bit. Here I am in my younger days at the World Championships of the Tug of War. Actually, of course, that's not me. That's, my head superimposed on some guy. You can tell because look at how dark my beard is, right? This was a few years ago when I made this diagram. I never actually have these tattoos on my arms here. But this tug of war is a good example of Newton's third law. Why? Well, there's a couple things going on. I am pulling to the right or backwards on the rope, and therefore by Newton's third law, the rope is pulling forwards on me, technically a force of tension. But what else am I doing? Right? If it wasn't for the what else that's going on here, I would just go forward. Right? Think about being on roller skates and pulling on this rope. Right? You would just roll forward as you pulled on it. But I'm also pushing on the ground. Now I'm going to have to push down and to the left. I'm going to combine those into one kind of force here. Right? So that's me pushing forward on the ground. So then what's the ground going to do? It will push backwards on me by Newton's third law with a force which is equal and opposite. So let's focus on me here, because after all, I'm what's important. Or at least that's what my wife would say, I thought. If I push harder on the ground than I pull on the rope, then the ground will push harder on me than the rope pulls forward on me, and I'll go backwards. So, in order for me to win the tug of war, I've got to be able to push harder than I pull. Back in the day when I was a younger, more nimble teacher, I used to like to go down during the tug of war during homecoming and scream at the senior class to push harder. Those that were in my class understood. The rest thought I was some moron that was yelling at them. But the ones that were in my class understood that they had to push harder on the ground. Now, one year I was sitting up in the stands with a few of my colleagues, Mr. Weston among them, and I saw the two classes go out there, and I said to him, uh-oh, the seniors are going to lose this year. And in fact, they did. And I knew that they were going to lose because what happened was that the underclassmen took their shoes and socks off, and the seniors left their shoes on. Now, the seniors were bigger and stronger and could probably pull harder than the other class, but they couldn't grip the floor very well. If you've ever been on the gym floor in gym shoes, you often get this little layer of dust that builds up, and so that is really slick. That's why basketball players are always licking their fingers and rubbing the bottoms of their shoes and things like that to give them a little more grip on the floor. Right? Well, the underclassmen with their shoes and socks off, you get really grippy on a gym floor like that. So they were able to push a lot harder. So the seniors kind of pulled themselves forward, actually, and lost the tug of war. So it's really all about how hard you can push compared to how hard you have to pull. So there's some complications with Newton's third law. Feel free to rewind and try to wrap your brain around those. Even though the law itself is fairly simple mathematically, there are some complications, and you have to involve the others of Newton's laws.